Let's start by understanding what exceptions are. Exceptions are sudden events that cause the processor to temporarily stop what it's doing and execute a special handler function. When an exception occurs, the current task is suspended, and the processor jumps to the exception handler. After the handler finishes, the original task resumes exactly where it left off. These handlers are often called interrupt service routines, or ISRs. In the ARM architecture, interrupts are one type of exception, typically generated by peripherals or external inputs. Next, focus on interrupts are a common exception type. Interrupts allow the microcontroller to respond quickly to real-time events, like a button press or data arriving on a communication bus, without constantly polling. This diagram illustrates several exception sources in a Cortex-M system: peripherals, system timers, and on-chip fault detection, all feeding into the Nested Vectored Interrupt Controller, or NVIC. Now let's look at the different exception types a Cortex-M processor can handle. This table shows all exception sources, from number 1 to 15 and beyond, along with their priorities and functions. Notice the priority levels. Reset has the highest fixed priority at -3, followed by the non-maskable interrupted -2, and hard fault at -1. The rest are settable. For system exceptions like SysTick and PendSV, the CMSIS interrupt numbers are negative. But external interrupts start from 0, making the numbering different from the exception numbers in the vector table. Next, focus on CMSIS interrupt numbers for system exceptions are negative. This distinction is important when using the CMSIS device driver library, where interrupt numbers begin from 0 and system exceptions have negative values. The function column briefly explains why each exception might occur, for instance, a bus fault from an invalid memory access, or a debug monitor triggered by a debug event. It's worth noting a few more key points about exceptions. The numbering you see in the vector table is not the same as the interrupt numbers used in the CMSIS library. In the CMSIS device driver library, system exception numbers are negative, while they are positive in the hardware vector table. This mapping helps software development but can be confusing at first. Unlike classic ARM processors such as the ARM 7 TDMI, Cortex M3 and M4 do not have a fast interrupt, or FIQ. Instead, they achieve remarkably low interrupt latency, only 12 clock cycles, making FIQ unnecessary. Finally, the reset exception is special. When the processor exits reset, it runs the reset handler in thread mode, not handler mode like other exceptions, and the interrupt program status register reads as 0. Now let's meet the core component that manages all these exceptions, the Nested Vectored Interrupt Controller, or NVIC. It is built into every Cortex-M processor. The NVIC is programmable, and its registers are located in a dedicated memory region called the system control space. This memory-mapped approach makes it easy to access from software. It handles all exception and interrupt configurations, enabling or disabling interrupts, setting their pending status, assigning priority levels, and applying interrupt masking. The NVIC has 4 main features: flexible interrupt management, support for nested exceptions, vectored exception entry, and interrupt masking. Let's explore each one. The first feature is flexibility. The NVIC allows you to individually enable or disable every interrupt except the non-maskable NMI. You can also set or clear the pending status of an interrupt through software. Interrupt sources can be of 2 types. A pulsed interrupt is at least 1 clock cycle long. When the NVIC detects a pulse, it sets the pending flag and holds it until the interrupt is serviced. A level-sensitive interrupt, on the other hand, keeps the request line high until the interrupt is acknowledged. The signal level at the NVIC input is always active high, but the actual external pin may use different logic levels, handled by on-chip circuitry. This versatility means the NVIC can seamlessly handle interrupts from a wide variety of peripherals and external devices. The second major feature is nested exception support. Every exception has a priority level. For most interrupts, this is programmable. For critical ones like NMI and hard fault, the priority is fixed and very high. When an exception occurs, the NVIC compares its priority with the priority of the currently executing code. If the new exception is not more urgent, it will be held pending until the current task completes. But if the new exception has a higher priority, the NVIC immediately suspends the current task. This process is called preemption. The processor automatically saves critical registers to the stack. This is context saving. Then, it vectors to the new exception handler. Once that handler finishes, the processor restores the saved context from the stack and resumes the preempted task exactly where it left off. This allows unlimited nesting of interrupts. The third key feature is vectored exception entry. When an exception occurs, the processor needs to know where the handler is. Instead of using slow software lookup, Cortex M automates this entirely. Traditionally, in older ARM processors like the ARM7 TDMI, software had to read a register or poll to determine the handler address, which added delay. Cortex M uses a hardware vector table stored in memory. Each exception has a fixed entry in that table, and the processor reads the handler address directly from it. This vectored approach eliminates any software overhead, drastically reducing the time from the exception event to the execution of the handler. This is a major factor. Sometimes you need to temporarily block interrupts, for example, during a time-critical operation. The NVIC offers special masking registers for this purpose. The PriMask register can disable all exceptions except hardfault and NMI. It's a simple global switch. The BSEPRI register is more selective. It masks only exceptions with priority at or below a threshold you set. This masking is critical for sections of code that must not be interrupted, such as updating shared data structures or handling precise timing sequences. To make this easy, CMSAS Core provides functions like __disable _IRQ and __set BSEPRI, allowing you to manage masking without directly accessing the hardware registers. The vectored entry relies on a data structure called the vector table. Here it is. The table is simply an array of 32-bit words in memory, each slot holding the starting address of a specific exception handler. After reset, the vector table starts at address 0. The first entry is not a handler address but the initial value for the main stack pointer. The real vectors start at offset 0x04, the reset handler address is stored there. Each exception type gets a word, NMI at 0x08, hardfault at 0x0c, and so on. The address is simply calculated as exception underscore number times 4. Next, focus on, example, reset vector at offset 0x04, 1 by 4, comma. The table is relocatable. By writing to the VTOR register, you can move the entire vector table to a different memory region, such as internal S or AM, for more flexible system design. The vector table offset register, VTOR, allows relocating. When something goes wrong, the processor uses fault exceptions. This diagram shows the fault handling mechanism. The Cortex M3 and M4 have 4 fault exceptions, but by default, only hard fault is active. The 3 configurable fault exceptions are MEM Manage, which catches memory protection violations, bus fault, triggered by bus errors, and usage fault, for undefined instructions or other misuse. Out of the box, these handlers are disabled, so any fault event escalates to the hard fault handler. This ensures you always catch errors, but with limited detail. Next, focus on, enabling individual fault handlers provides detailed error. You can enable individual fault handlers to get more specific information about the error, like the instruction address that caused the fault, and even attempt recovery before the system fails. The image illustrates the fault handling flow. Finally, let's briefly touch on the System Control Block, or SCB. This is a set of registers closely associated with the NVIC, also located in the system control space. The SCB controls processor-wide configurations like low-power modes and provides fault status information through registers such as the bus fault address register. One important SCB register is the VTOR, which we just discussed, used to relocate the vector table. Other registers hold detailed fault reports. Full details on the SCB are covered in later chapters of the reference manual, but this introduction gives you a foundation for understanding system control.